SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We were looking at the cylindrical shell geometry, and initially I said I will derive the equations of motion in terms of the force resultants, and we did the x and theta equations. Okay, so let's move on to the U3 equation, and I said I am going to take theta as alpha 1, d theta by 2, d theta by 2. Now what are the relevant force resultants? So we will have q theta 3, the incremented q theta 3, okay. Let me write the full form. Del theta q theta 3 d theta, then the other qx3 qx3 plus del x qx3 dx. What else contributes? We have n theta theta, incremented value n theta theta plus del n theta theta by del theta d theta. Okay, so that's about it for the alpha 3 direction. Alpha 3 direction. So what do we have? We have minus qx3, okay, into a d theta, full force, plus qx3 plus del by del x qx3 dx into a d theta, now a full force, okay. Then we have q theta 3, okay. How does q theta 3 move? Okay, if I place my coordinate axis there, then I have d theta by 2, d theta by 2, okay, q theta 3, then q theta 3 plus del theta q theta 3 d theta, okay. And we are looking for vertical direction, so let's break that up. vertical, horizontal, vertical, horizontal. This time they are opposed. Okay, this time they are opposed, and if this is d theta by 2, this is d theta by 2. So I need the cosine of that angle, okay, which is that itself, right, for small angles. So I get minus q theta 3 into dx, a full force, plus q theta 3 plus del q theta 3 by del theta d theta into dx. That's about it. Okay, so then this cancels and we get this remainder. Okay, that is the q theta 3 resultant. Now one last term is n theta theta. Let me try it out here. So if this is the element n theta theta, n theta theta, n theta theta plus del n theta theta by del theta d theta. Okay, so now this has a vertical component, horizontal component, vertical component, horizontal component. The vertical components are now adding. Okay, that's my alpha 3. However, it's in the negative direction. Okay, so what is this angle? This angle is d theta by 2. So therefore this angle is d theta by 2 and that angle is d theta by 2. So I am looking for the sine component of it. Okay, I am looking for sine component of n theta theta. Okay, so this will be n theta theta multiplied by dx d theta by 2 with a negative value. Same thing here, but this is a small order term, so we can neglect it right away, and this will double. Okay, so if we add all the terms up, what do we get? We get del x qx3 dx into a d theta, okay, plus del q theta 3 by del theta d theta dx minus n theta theta, okay, into dx into d theta is equal to rho h a dx d theta u3 double dot. So if I again divide by a d theta dx, okay, I get del qx3 by del x plus 1 over a del q theta 3 by del theta minus n theta theta by a is equal to rho h u3 double dot. That's the third equation of motion. Okay. Now let's look at maple again. As I spoken before, we have acquired this maple 22 on a 15-day trial. So here if I turn on the cylinder related Lemay parameters and radii of curvature, I will get cylinder equations. So let us run those. Okay. Okay, these are the 3 cylinder equations. Okay, so this is the axial equation, this is the torsional equation, this is the transverse equation, In each of these you will find u1, u2, u3, so they are all coupled. Okay. I have told you earlier about the ring issue, which is a one dimensional structure. Okay. So, this 1 minus u square goes away, this becomes rho a, okay, and an extra b comes here. So, EBH cube by 12 and EA. Okay. So, now for the cylinder, if I increase the font now for increase the font. So, now you can see that there is a temporal derivative term here, there is a temporal derivative term here, and there is a temporal derivative term over here. Okay. Now, if we substitute the correct mode shape, okay, it will turn out into an algebraic equation. Okay. The mode shapes together will be cancelled from both sides and it becomes an algebraic equation, and this term will end up as a diagonal. The temporal term will come on the 3 diagonals, okay, and double derivative with time will become omega square. So, you will have omega square on the 3 diagonals, it is a 3 by 3 matrix. Hence, what we will have is a cubic in omega square. Okay. So, we will have a cubic in omega square. So, we will have 3 sets of natural frequencies, okay, and each set will be dominantly related to axial movement, the second set dominantly related to the torsional movement, and the third set dominantly related to the transverse movement. Okay. So, we will work with this set of equations in the lectures. I will continue with the lectures now. These are the 3 equations. Okay. So, we get the first equation, let us say it starts to look like K. So, I will represent K represents EH by 1 minus mu square, it is the membrane stiffness. Okay. And D is E H cube by 12 1 minus mu square, which we will call the bending stiffness. Okay. So, the ux equation of motion, ux. Okay. So, what is ux? So, we have this shell, so I will get back to my x theta coordinate, x is this way, theta is that way, alpha 3 is that way. Okay, x theta. So, the x equation of motion now is k times del 2 u1 by del x square, or u1 is ux. So, ux plus k times mu del 2 u theta r del x del theta plus 1 over r del u3 by del x plus, okay, k into 1 minus mu by 2 del 2 u theta r del x del theta plus 1 over r square del 2 ux by del theta square, okay, is equal to rho h ux double dot. Okay. Now these two can be further combined. Okay, I am not combining those, but those two can be further combined. Then in the u theta direction, what do you get? You get d, okay, let this be, we will stick with a for the radius. Then we have d over a square plus k into 1 minus mu by 2 into del 2 u theta del x square, okay, plus k into 1 plus mu by 2 1 by a del 2 ux by del x del theta, okay, plus d by a square plus k into 1 by a square into del 2 u theta by del theta square, okay, minus d del 3 u 3 del x square del theta, okay, plus k over a square del u 3 by del theta minus d by a fourth del 3 u 3 del theta cube, okay. This is equal to rho times h times u theta double dot. And lastly, we have for the u3 equation, okay, we get minus d del 4 u3 by del x4 minus 2 d over a square del 4 u3 by del x square del theta square minus d by a fourth del 4 u3 by del theta 4 minus k u3 3 over A, okay, then plus d over A fourth del 3 u theta by del theta cube minus k over A square del u theta by del theta plus d over A square del 3 u theta by del x square del theta minus k mu by A del ux by del x, that is equal to rho h u3 double dot. Okay, so these are the three equations of motion for the shell. Okay, now as we did for the ring, our objective initially is to find the mode shapes. And natural frequencies. Okay. So now we will for a simply supported shell, cylindrical shell. So now if this is the shell, then the simple support implies here that your u3 is 0, okay, then u theta is 0, that means this movement is also arrested, and nxx is 0, it is free, it's free along this direction, nxx is 0 and mxx is 0, it is free to rotate, okay, this rotation is allowed. Okay, so u3 must be 0, u theta must be 0, nxx must be 0, mxx must be 0, and repeat the same conditions repeat over here. Now in practice, how do you get this? You can get this if you have a cylinder and you put a reasonably rigid lid here, bolt a lid over here. Okay, so what that lid will do is it will prevent u3 movement, because it's a, it's stiff in plane extension, and it's stiff in rotation, so it will prevent u theta movement also. Okay, and because it's just at the edge, okay, it will not prevent axial extension, and therefore nxx is 0, and it will not prevent rotation, and therefore mxx is 0. Okay, for this situation, if we now assume, just as we did for the ring, a certain a mn cos m pi x by L cos n theta, then for u theta we assume Bmn sine m pi x by L sine n theta, and for u3 some Cmn sine m pi x by L cos n theta, then the three equations are exactly satisfied. These three equations will exactly be satisfied. Okay. Of course, we will put an e to the power of j omega m n t, j omega m n t, j omega m n t for the frequency or temporal part. Okay. Now, as I said for the ring, this relationship, that this should be cos and this sine and this cos, that is decided by the PD. Okay. However, there has to be a parallel sine n theta, cos n theta and sine n theta mode also. Okay. So, there are two sets of modes, okay, and these are orthogonal. This is orthogonal to this, this is orthogonal to this, this is orthogonal to this. There are two sets of modes, okay, and both will have the same natural frequency. We saw that for a ring, natural frequency determinant did not change. Okay. So, now let us plug in one set, let us plug in one set. Okay. So, if we plug in one set, what happens is we will now get a matrix, a coefficient matrix, and it somewhat looks like rho h omega mn square minus k11, k12, k13, k21, rho h omega mn square minus k22, k23, k31, k32, rho h omega mn square minus k33, this has to be 0. Okay. And for non-trivial values of amn, bmn and cmn, the determinant of this matrix has to be 0. Okay. And that ends up giving us a sixth order equation in omega. Okay. So, we get omega mn sixth plus a1 omega mn fourth plus a2 omega mn square plus a3 equal to 0. Okay. And it's actually a cubic, it's actually a cubic. So, you can solve for it. Okay. So, you get omega 1 mn squared, you get omega 2 mn squared and omega 3 mn squared set of natural frequencies, natural frequency. Okay. What are these omega 1, 2, 3? Now, the shell itself is capable of moving in 3 directions. Okay. Any point on the shell is capable of 3-dimensional movement, right. A single point can have ux movement, can have u theta movement, it can have u3 movement. Okay. So, you will have natural frequencies that are related to each movement. So this could be u1 square mn, this could be 2 mn, this could be 3 mn. That means with this set of natural frequencies, the shell dominantly vibrates with axial movement. That means for every point the dominant movement is axial. Okay. There can be a little bit of theta and u3 because it is a coupled system. Okay. But dominant movement is in the x direction. Similarly, these set of natural frequencies could be dominantly vibrates in the u theta, and the last one dominantly vibrates with u3 movement. Okay. But how will you know? How will you know? How will one know which set? The way to know is once you have your natural frequencies, these are now in a closed form. If you look at the textbook, you will get the closed form equations and you can plug them in MATLAB and get the. If you plug any one of this set, okay, now that it is a eigenvalue, the matrix is singular, okay, which means you can use any two of the equations. Okay. So now you could represent AMN and BMN, let us say in terms of CMN. Okay. So then you will have or let me say that you could represent CMN and BMN in terms of AMN. So you will have CMN by AMN, BMN by AMN for the omega 1 Mn set of natural frequencies. Okay. Now if you find that this value is small and this value is small, then what that means is AMN is larger. That means these are dominantly axial, or x direction. Similarly, you could plug in the omega 2 set of natural frequencies. Those are also eigenvalues. So the matrix is singular, and then you could represent any two values in terms of the third. So let us say we represent CMN and AMN in terms of BMN, then we get CMN by BMN and AMN by BMN, and let us say these are very small. That means BMN is dominant, which means these are dominantly torsional set of natural frequencies, and similarly the omega 3 Mn. Now the shell is quite stiff, even though it is thin. Shell is quite stiff in the axial and torsional directions. Okay. So typically the x and theta natural frequencies are high. And so the u3 or alpha 3 direction natural frequencies are the lowest natural frequencies, lowest set of natural frequencies. Okay. Now we have run out of time, and so what I will do is I will stop it here and continue this topic in the next lecture. Okay. Thank you.